Good. So last time we left off with, I think, a pretty good foundation of what goes on with nucleophilic addition reactions to ketones and aldehydes. We saw several that we were already familiar with, like hydride reduction, like the addition of Grignardin or alkylithium reagents to make alcohols. So those are also examples of this type of reaction. And we also went over the hydration of aldehydes and ketones under either acidic or alkaline conditions, a reaction that is otherwise useless synthetically, but is helpful to go over because by it we learn how to think about reactions of that type in either acidic or alkaline conditions. I should also mention, once again, of course, I am not taking attendance. I'm not allowed to do that until first thing tomorrow morning. So there's no attendance today. I guess I won't do it on Friday either, since we're taking an exam. So the earliest I'll be doing that again is Monday, next Monday. Good. Now, we did mention last time about cyanohydrins. This is the result of net addition of HCN to an aldehyde or ketone, and I have here just a generic aldehyde or ketone. If you treat an aldehyde or ketone with either aqueous HCN with a little bit of hydroxide in it as a catalyst, or frankly, you could also use, and you might also be given, just sodium or potassium cyanide and H2O. It'll still work. Same mechanism, everything's the same. In the end, you get a compound of this type, which is known as a cyanohydrin. And these are actually kind of useful. There's things you can do with the nitrile functional group. The mechanism's pretty straightforward. Here I'm using acetophenone just as an example of an aldehyde or ketone. And I go over down here some things that you should do in terms of practicing, also some information on what you do and do not have to put down. But please do refer to those. I'm trying to make it as easy as I can in terms of what to do to practice. Of course, for exam 2, this is all going to be in exam number 2. In any case, since we're in alkaline solution, well, let me not go that far. How do I know that I'm in alkaline solution? Am I in alkaline or acidic solution? When I look at what I'm given, I see hydroxide mentioned. That's enough of a tip-off that we're in alkaline solution. Even if hydroxide were not given, and instead we had, say, NaCN and H2O, that's still enough to let me know that I'm in an alkaline solution, because I don't see any strong acids mentioned. Sodium cyanide isn't exactly a really strong base, but it's certainly not an acid. And when you have only that and water, then we have to be under alkaline conditions. So that's how I know that I'm working on the alkaline side. Always it's by looking at what you're given. It's not something memorized ahead of time. It's something that's situational, that you always decide at the moment, depending on what you're given. Since we're under alkaline conditions, we're perfectly reasonable, assuming there's going to be some cyanide ion around. The hydroxide ion will deprotonate some of the HCN, which also is not the strongest acid in the world, but with hydroxide around is strong enough. And again, if we were instead given KCN or NaCN instead of HCN without the hydroxide, well, that of course implies that the cyanide ion is present. So either way, we have cyanide ion present. That will attack our carbonyl. It will lead to formation of an alkoxide ion, which again, since we're in alkaline solution regardless, that's perfectly fine. Next, all we need to do is find a proton source to put the proton on that alkoxide and give us our neutral cyanohydrin. Water is perfectly fine. In either case, we'll have water, and I could see water being a reasonable proton source here. If you had also used an HCN molecule here, as I said in the class notes, I was pretty clear on what you should and should not put. But if you were to use an HCN molecule here, I would certainly have no objection. I'm sure both happen in real life. Again, HCN is by no means a strong acid, but it's a good enough acid to protonate that alkoxide. So either way, you're fine, and you wind up with the cyanohydrin. And now, unlike with the aldehyde hydrates, as we'll learn later, this is something we can actually work with. We already know, for instance, how to reduce a nitrile functional group from C triple bond N to CH2NH2. That's from chapter 24, the chapter on amines. So that's one thing we know how to do. We're also aware, though we don't know the mechanism yet, we will eventually learn it, that you can hydrolyze a nitrile to go from C triple bond N to CO2H. In that case, the nitrogen actually winds up in a molecule of ammonia. And like I said, we'll eventually learn that mechanism. That's probably round in about chapter 21 or thereabouts, somewhere in that range. So the reason we're going over this here is because this is another example of a nucleophilic addition to a carbonyl compound. And so it's relevant for that reason. And the reason you need to know this reaction is there's a bunch of other reactions in this chapter, all of which, at least on some level, are just like it. So all of the reactions we're learning in this chapter involve some sort of nucleophilic addition to either an aldehyde or ketone. So that's why you need to learn this here, and that's why it's relevant at the moment. Good. I can't really think of anything else to say, though. It's a fairly straightforward mechanism, just 2 steps in alkaline solution. So any questions then on cyanohydrins? And yes, you can maybe see Barnaby over my left shoulder, just barely. Someone has asked if we can have a CAT cam during the exam. I'll see what I can do. The exams will require that we show lone pairs. Last semester, my professor didn't require them. Well, there's no way to answer that question yes or no. There's no always and never type of thing. The rule that you should follow in terms of whether to show lone pairs is basically the common sense principle of, are they communicating anything that we really need to know about now? If you're using that lone pair in a mechanism, then you need to show it. If you're just drawing a group that's just attached and not doing anything at the moment, you don't need to worry about it. So it's not about following a rule, and it's not about my giving promises beforehand of what I will or will not take off points for. Besides, you know, if the grader takes off points and they did it wrong, you'll get them back. I'm not an unreasonable person. We don't expect you guys to take responsibility for grading mistakes. But I like how John put it just below. If it's relevant to the process, if it's communicating something important, then show them. But don't spend 10 minutes putting dots everywhere if most of those atoms are not doing anything. So the way to know what you need to put is by thinking about what you're trying to communicate. It's not by memorizing rules that are given beforehand. And I'm not trying to jump on you here, you know. It's the sort of thing that a lot of students are wondering. But what I'm trying to encourage you guys to do is to understand that it's, again, as always, a different type of learning process with organic chemistry. But I think John said it best. If they're relevant, show them. If not, don't bother. Really, the only time I make showing all electron pairs, all lone non-bonding electron pairs, the only exam that I do that for is actually exam 1 in organic 1. That's the only time I'm really picky about it, because we're still learning. After that, we can be a little bit flexible. But at the same time, like I said, you guys need to learn to be comfortable with a little bit of flexibility, that not every single little rule is explicitly stated. From my experience, last semester, it's extremely obvious when you need them. You won't be able to complete the question without them when you need to show them. Yeah, and I think really already at this point, you guys already know when you need to show them and when you don't. It's mostly a question of mechanisms, and you of course need to show all reacting electron pairs. But if there's other electron pairs elsewhere that are not involved, you can draw them, sure, but why bother? Good, so I think we already said all that. For the remainder of the class time, I want to go on to considering nitrogen and oxygen nucleophiles, adding to ketones and aldehydes. and we'll talk about the formation of imines or Schiff bases. They're also called enamines, and also acetals. That's going to be, and honestly, I think that'll be enough. That'll probably take us all the way to, if not 1250, at least like 1245. Good. So I'd like to start with nitrogen nucleophiles, so there's no reason to go in any particular order. Amines can react with aldehydes and ketones under acidic conditions. These generally require acidic conditions. Certainly, I think they work better under acidic conditions. And it all depends, though, on what type of amine we've got. Of course, amines can be primary, secondary, or tertiary. And again, please do review that if you've forgotten those terms. That's in chapter 24. I go in kind of an interesting order here, but I'd like to go from the simplest case to the most complicated case. The simplest case is if the amine is tertiary. In that case, game over. There's no irreversible reaction possible. Sure, you can have the tertiary amine add to your carbonyl carbon, but then nothing further can happen, so it just falls back off. So you don't get an irreversible reaction when the amine is tertiary. That's the simplest case. Tertiary amine, game over. No irreversible reaction. If the amine is primary, that's the second simplest case. Then again, in the presence of an acid catalyst, you will get a type of compound known as an imine. The biochemists call these Schiff bases. You need to be very careful when you say Schiff bases. But be that as it may, you do wind up also with a molecule of water as an inorganic side product. And in fact, it's the oxygen and the carbonyl that winds up in the molecule of water. And there's no need to memorize that. You'll see it when you look at the mechanism. It just stands right out from the mechanism. Again, I want to stress two things. First of all, there is acid present. So probably the way you do this is you take your aldehyde or ketone. I'm just using here acetophenone again. Once again, is just an example. I could have picked any aldehyde or ketone. So you'll dissolve that in your primary amine. Here I'm using butylamine just because it came to mind. I could have picked any other primary amine. And you would probably add a little bit of some strong inorganic mineral acid, a few drops of sulfuric acid, concentrated sulfuric acid, or maybe HCl. I think any of those types of acids will work. And it may tell you what the acid is. It may say H2SO4, for example. So you know, the old exams and the OWL problems, which I'll probably make available like this weekend. Let's get through the exam first before we worry about chapter 19 OWLs. But be that as it may, that will give you some ideas about how this might or might not be shown. In the end, you replace the carbon-oxygen double bond with a carbon-nitrogen double bond. And that's going to be our major organic product. Good. So as I'm pointing out here, before we even get into the mechanism, let me also draw attention to what is not here. Please notice it does not mention water. And indeed, these are done under anhydrous conditions. So you don't have either water or H3O plus here. In fact, I would expect that if you did the reaction under even somewhat aqueous conditions, you would get a very low yield at best, because Le Chatelier's principle says that when you add more of one of the products, you drive the equilibrium backwards. So really, for this reaction, we need to exclude water. And so, yes, you do get one molecule of water out at the end, but that's then going to be lost in this ocean of the primary amine, and it's effectively as though it were removed from the solution. And in fact, there are ways of literally physically removing the water from the solution also. But even if you don't, I would expect the reaction to be driven strongly to the right, because even if you don't literally physically remove the little bit of water you get, when it's dissolved in this ocean of the primary amine, it's a non-factor. So that's one of the reasons that the reaction is driven forward. So we need to get down, again, that we focus on what we're given. We're given the ketone or aldehyde, we've got our primary amine, and we've got a catalytic amount of some acid. Now, what's that acid going to do? Well, if it's an acid like H2SO4, HCl, one of these strong acids, of course, it will dissociate completely. and you'll be left with some of the primary amine molecules getting protonated to generate the conjugate base, which I talk about over here. In fact, that's what we will use as our proton source rather than H3O+. We can't use H3O+ because we don't have water around, and the way we know is by looking at what we're given. That's the main thing I need to stress here. Always look at what you're given and make sure that anything you draw makes sense in light of that. So essentially, we've got the carbonyl compound, our primary amine, a little bit of the conjugate acid of the primary amine, and I suppose you also have the conjugate base of whatever your strong acid was, right? If it was sulfuric acid, you'd have some bisulfate ions, HSO4-. If HCl, you'd have chloride ions, none of which matters. Those are just spectator ions. They're not going to play any role in the chemistry. So in terms of the mechanism, this is very standard for mechanisms of this type, and we're going to see this type of thing again and again. First thing we need to do is to protonate that carbonyl oxygen. Why? Because if we don't, then after our nucleophilic attack, we'll have an alkoxide ion, O-, and that's no good in an acidic solution. Remember, we don't want to use any strongly alkaline species in an acidic solution, which, looking at what I'm given, we're clearly in. So we need to put the proton on that oxygen first. Now, what do we use to put that on? Well, H3O+, right? Because I memorized it. Of course, it's not that simple. You always need to use species that make sense based on what we're given. I'm not given water over here. So any water there is going to be present in a vanishingly small amount. So we will instead use the conjugate acid of the amine. And here I'm using this particular species because butylamine happens to be my amine. If it were a different primary amine, then this would be a different species here, just as if this were a different carbonyl compound that I'm given, I would use whatever that is and then carry it through. So we protonate our carbonyl oxygen, just like we will tend to do in an acidic solution. Then we can have attack by our nucleophile. And right now, the most nucleophilic species is the primary amine. That will attack the carbonyl carbon and break the pi bond and get rid of the plus charge in oxygen. Now, why do I not use BuNH- over here? Why can't I? How do you know that we can't use the conjugate base of this species? Well, I think you'll agree. I mean, BuNH- is a thing, but it's also a very alkaline thing, very, very strong base. I mentioned this, and I'll give some more examples as we go on. Students, in my experience, find all kinds of ways to try to save themselves steps on the exam, to try to make it so that they don't have to write as much and can save some time. And that's all great if it's based in reality. Using BuNH- so that you don't have to show this type of intermediate isn't based in reality. We don't have any BuNH-. There's no way that can exist in even a neutral solution, let alone an alkaline solution. Right? So you need to use species that make sense based on what you're given. That's the main thing I feel I need to stress, just based on years of experience of grading exams. That's the most common kind of error, and the one most easily avoided by thinking critically, not just memorizing, not just regurgitating, but by thinking critically about what's going on in the solution. Even if you're given species you've never seen before, you'll be able to then predict what will happen. Good, so we get this intermediate here. Next, we're going to run into a couple of proton transfers, and those are really common in solutions, in acidic solution. Remember, the way I put it the other day is I generally find reactions in basic solution more straightforward, less steppy. That's because you don't have as many proton transfers necessary. But in acidic solution, we need to move around protons quite a bit more, just to make sure that we always draw species that make sense. So first thing we need to do is pull a proton off that nitrogen. And the way you know that you need to do that is by looking at the structure of the product. Those protons are gone. So one by one, they're going to have to be removed. So always look at what you're given. Every time you're writing a mechanism, every step you write should not be regurgitating something you memorized. It should be thinking critically about what's going on in this particular situation and how it relates to one of the general forms of something we discussed in class most likely. Good, so what are we going to use as our base? Well, the most basic material around is the amine. Again, always look back at what you're given. And all I see around that I can use as a base is just our amine. So that will surely be what does it. Then we need to put a proton on that oxygen in order for us to be able to lose water as a leaving group. That's that one water molecule you get that then gets washed out in this ocean of butylamine. And the only reasonable acidic species we have around in any quantity, again, is the conjugate acid of the amine. And the way you know that you still have that is, look, we just made one, by the way. Right, here's our amine that pulls off a proton. Doesn't that make this? These are the things that you can look at to help you to know what's around and why they're around. Now, I don't promise this ammonium ion is exactly the one that came from this. Why can't you just use the H+? Because there's no such thing really as just H+ floating around in solution. And you might have had some organic professors that allowed that without loss of points. I do not allow that here. And you can tell that by answer keys of old exams of mine. But there really is no such thing as just H+ floating around. It has to come off of something. So you don't have just H+ floating around by itself. And that's pretty well determined experimentally. Even in water, you don't have H+s floating around. You've got H3O+ ions. So that's an important principle. You do need to show the H+ always is coming from something. And you will always be able to know exactly what it comes from if you approach each mechanism the way we're doing here. So hopefully that satisfies your question. But that's why there's always something that it comes off of. And I think in general, we're able to know just what that is, or at least what a likely candidate for that species is. So just like we used the conjugate acid of the amine over here as our acidic species, we'll do the same over here. That puts a proton on this oxygen, and now we're able to lose a water molecule. Now, why did we have to do that? Why can't I just skip ahead and lose OH-? This is the sort of thing that you'll need to encounter and grapple with as you learn reactions, so that you'll be able to write it correctly. And the reason that we need to do that, again, is because we're in acidic conditions. And we're not going to be able to lose OH- as a leaving group, not in acid. In alkaline solution, yes, but not in acidic solution. And again, the way we know it's an acidic solution is by looking at what we're given. And so hydroxide is a terrible leaving group. And the only time it can act as a leaving group at all is if the solution is strongly alkaline, which based on what we're given, it's not. If anything, it's slightly acidic. So that's why we put that proton on. And if you know that, that's how you'll be able to remember it. Is that H+ at the beginning? You mean this one here? You automatically get this. And I put in the class notes what you have to show, by the way. I went over all that there. But yes, you automatically get that for free. I'm not sure this is what you mean, though. This first proton does come from the conjugate acid of the amine. And that you automatically get by adding a little bit of strong acid to the amine. So I would say these mechanisms in the class notes, I try my best to make them consistent with what you need to show on exams. I try my best. Of course, that's always somewhat situational. But yes, that gets thrown in for free. That reminds me of something else. Don't let me forget to prove to you that this reaction is acid catalyzed. That's not a bad exercise. Good, so once we protonate that oxygen, we can lose water as a leaving group, and we can in fact help push the water out using the lone pair on nitrogen. If you were not to draw that arrow, it would still be correct. You just get the other resonance form of this. In that case, you'd have your nitrogen with a lone pair and the plus charge in carbon. And remember, whenever you're dealing with a resonance stabilized species in a mechanism, it does not matter which resonance form you use. It's always going to be possible to draw a correct mechanism from any resonance form. So that would certainly be fine. That variant would be just fine. That's probably another case of not only would I not take off points, I wouldn't even notice. It's just the same thing. Good, so we lose our water molecule and we get now this species, and now all we need to do to get our neutral imine product is just pull off that proton. And again, an amine molecule will be more than good enough to do that. Remember that the water molecule that we just made is outnumbered probably by about, I don't know, 10 to the 18th, 10 to the 20th power to 1 by butylamine molecules. So it makes sense to use that as our base here. Now again, so we are told this reaction is acid catalyzed. That means that we should find that we're completely even at the end in terms of protons, that we neither use up a proton nor spit out extra protons that weren't there before. So this is always a good exercise, never a bad idea when you're looking at an acid catalyzed reaction to prove to yourself that it is. So over here, I'm taking a proton from you. So I now owe you a proton. Here, this adds, no proton transfers. Here, I'm paying you back your proton. Here, I'm immediately borrowing another proton. Then this goes on. And then finally, I pay you back the proton I owe you. So we're good. This is an acid catalyzed reaction. There's no H pluses either generated or consumed in a net sense. Good. Now, I also want to point out that there's exactly what defines an imine. We gave the definition of an imine by a structure. We defined it by a picture. So an imine is a compound of this type, and it basically means that you've got a carbon-nitrogen double bond. It's essentially what you get when you replace the oxygen of a ketone or aldehyde with nitrogen with an alkyl group on it. So always, if you're in the class notes and you don't see something defined in words, it's probably defined in a picture. And so we've defined it back here. Good. Oh, while we're on the subject of imines, you'll find a table of several other compounds, and they have funny names. These are your oxenes, your hydrazones, your acethydrazides. There's all of these other ones, and honestly, they're only special imines. There's otherwise nothing different about it. The only difference is what is attached to the nitrogen, is what you have attached to the nitrogen of a primary amine. If instead of an alkyl group, you've got OH attached to the nitrogen, that compound's called hydroxylamine, and you will wind up getting what's known as an oxene. And hydrazones are another variant on it, acethydrazides also. But the main thing to focus on is they're just special imines. The mechanisms for forming them are exactly the same. And so there's nothing extra that you'll need to know other than the same mechanism. So the mechanism of formation of all of these other ones is exactly the same as the mechanism we just went over. The only difference is what's attached to the nitrogen here. They're just specialized forms of imines. Good. Where are we at? 12:30, so we got 20 minutes. Good. Everyone okay with imines then? If you're okay with imines, then we have just one category of amines to consider, and that's secondary amines. Secondary amines can also react with aldehydes and ketones, but only if the aldehyde or ketone has at least one alpha proton. The definition of alpha is next to. So if that's something new or you forgot about that, please write that down. Alpha means next to. In other words, we need to have at least one proton on a carbon next to the carbonyl carbon. So not coming off the carbonyl carbon. I'm not talking aldehyde protons. But you need to have at least one alpha proton, meaning it's on the carbon next door to the carbonyl carbon. You need at least one. If you don't, again, you won't get an irreversible reaction. But as long as you have at least one, you're good to go. And of course, here we've got 3 alpha protons. And so the type of compound you get in that case is called an enamine. And the definition of enamine is encapsulated in this structure. It's basically as you see. It's really exactly what it sounds like, enamine, right? It's kind of like an enol, except it's an enamine. You've got a nitrogen there. And here I'm using acetophenone again, just as an example of an aldehyde or ketone. I could have picked any other. Here I'm using diisopropylamine. I could have picked any other secondary amine. Once again, there's going to be an acid catalyst, and once again, we will form one molecule of water for every molecule of the aldehyde or ketone that reacts. So most of the mechanism actually is exactly the same. It starts out again by protonating that carbonyl oxygen. The way I know I need to do that is because I'm in acidic conditions based on what I'm given. What do I use as my proton source? Well, nothing other than the conjugate acid of whatever the amine is that you're given. Here, my amine is diisopropylamine, and so the conjugate acid looks like this. So that's going to pull a proton off of the conjugate acid, protonate my carbonyl oxygen, and then once again, my nucleophile can add, my nucleophile being the amine. You get an intermediate of this type. By the way, IPR stands for isopropyl. If you'd rather just draw it out, that's fine too. I was just feeling particularly lazy. But once again, we have to do a couple of proton transfers. First, we know to get rid of this proton so as to get rid of the plus charge on nitrogen. We'll just use an amine molecule in order to do that. That pulls off that proton. Then we need to put a proton in the oxygen. And the way we know that is because we need to get rid of that oxygen in order to form that water molecule at the end. And by the way, you may or may not be given that the water molecule is there. Always look at the directions, especially on OWL, in terms of what you need to show. Generally, they're clear, but it's also kind of in mouse print. So you need to be careful to read everything. But anyway, the next step is protonating this oxygen, just like before, so we can lose that water molecule. Here we are, we get this intermediate. This also is exactly the same. And we can lose this water molecule with help from that amino nitrogen. And it's only in this step, only this far in, that the formation of enamines diverges from the formation of an imine. If we were going to form an imine, then we'd use our amine base to pull a proton off that nitrogen to get rid of the plus charge. But there is no proton here. So we need another way to get rid of the plus charge. And another way is by deprotonating alpha to the formerly carbonyl carbon. So we use the amine to pull off one of these protons. The electrons in the carbon-hydrogen sigma bond then swing in and form a new pi bond between the carbons that also breaks the carbon-nitrogen pi bond and neutralizes the plus charge on nitrogen. You get your enamine. So you do need at least one alpha proton for this reason. There needs to be at least one proton attached to the carbon next door to the carbonyl carbon. If not, then you can't get the enamine, and it will just revert back to the starting materials. So you do need, in order for a secondary amine to be able to react with an aldehyde or ketone, you do need at least one alpha proton. Here we actually had 3, but you need at least one. If not, then you won't get an irreversible reaction. It'll just go back to the starting materials. Good. I think that's basically it. So that's enamines for you, and that covers the 3 possibilities. Tertiary amines do not react irreversibly with aldehydes or ketones, even in the presence of an acid catalyst, game over. Primary amines, straightforward, you get the imine. Secondary amines will give you an enamine if there's at least one alpha proton on the carbonyl compound. And that's basically it. That covers all of the possibilities. Good. Questions on imines and enamines then? Well, I wasn't going to spend a whole lot of time on the Wolff-Kishner reaction, although it's kind of relevant, believe it or not, to chapter 16, because in chapter 16, we talked about making aromatic ketones with a Friedel-Crafts acylation, and then the possibility of reducing the ketone carbon all the way down to CH2. And this is yet one other way of doing that. And the way you do it is by making the hydrazone, which is pretty much the same mechanism as making an imine, except instead of like an alkyl group attached to the nitrogen is another nitrogen attached. So this compound is called hydrazine. It's pretty nasty stuff. This is usually done under basic conditions. You can make the hydrazone under either acidic or basic conditions. Acidic conditions would look exactly like the mechanism that we covered earlier for forming an imine. But when you then, make the solution alkaline then, generally this is done by adding a bunch of either sodium or potassium hydroxide and then cranking the heat up pretty high. And what happens is you reduce the carbonyl group all the way down to CH2, and the other byproducts are water. That's going to come during making the hydrazone. That the oxygen and the carbonyl goes into water. And you also get a molecule of nitrogen gas. And of course, those two nitrogens come from the hydrazone molecule. And that makes sense. We're reducing C double bond O to CH2. So that means something else is going to have to get oxidized, and it's going to be the hydrazine. So that's a very strong driving force of forming the nitrogen gas. The mechanism in the book is not wrong. I'm totally fine with that. I'm giving you another version that's also acceptable that you might prefer. This is after you actually form the hydrazone. So that part of the mechanism up till there is the same in either case. And by the way, that mechanism is again the same as forming an imine. Once though you get the, in fact, hopefully you can see this is really just an imine, except instead of an alkyl group, I've got NH2. But otherwise it's exactly the same. So they seem to have started their reaction with 2-pentanone, and they're showing how you can reduce 2-pentanone to pentane by first making the hydrazone. So again, the mechanism up to here is, again, I think best done in acidic solution, and it's the same, I should say, as what we set up here, exactly the same. Arrow for arrow, identical. Then when you add base, this hydrazone will now collapse and do so in such a way as to generate nitrogen gas and also form the alkane. So the first step, in the first step, your hydroxide deprotonates this, this primary amine group. And it only needs to do that in low concentrations, which it will do. But once you form that anion, that will very quickly form the nitrogen-nitrogen double bond and break the nitrogen-carbon pi bond, and that can at the same time pick up a proton from water. That then basically happens again. Hydroxide now pulls off that one remaining proton. You get this type of anion, and this is just one bond shift away from forming molecular nitrogen. So we form that second pi bond, we break the nitrogen-carbon bond, and it actually involves losing a carbanion as a leaving group. Now, I can hardly imagine a worse leaving group than a carbanion. It doesn't get any worse than that. But when you're forming a nitrogen molecule, it's good enough. So, so again, deprotonation, formation of a pi bond, protonation over here, deprotonation again, formation of another pi bond, and then loss of, by the way, this is all already in your class notes. I hope you don't mind my just using the class notes since it's already all written down, but all of those structures are already in your class notes. So we then lose a carbanion as a leaving group, which is bizarre, but since we're forming nitrogen gas, it's good enough. And that will, of course, very quickly pick up a proton from water, which is present, and you get your alkane. So this is just an example of, I really also should have written OH minus and H2O, because really that's also present. But all that information is in your textbook, and you may prefer the mechanism in your textbook. It's not wrong, it's perfectly fine. This one might work better for you though, and if you like that one better, I have no objection. I would bet you anything both actually happen in real life. So, so much for the Wolff-Kishner reduction. I'm basically leaving you to read about that on your own, but I'm just clarifying the mechanism a little bit. And some of you might like that mechanism better, in which case go for it. Good, so that leaves only the issue of acetals and hemiacetals, which is what we encounter when we treat an aldehyde or ketone with an oxygen nucleophile, namely an alcohol. So any questions before we do that on imines, enamines, hydrazones, the Wolff-Kishner reduction? By the way, we know all kinds of other ways to effect that transformation. What about catalytic hydrogenation? Also works. There's also one involving acid and either an iron or tin reducing agent. So that's also fine. This is just another way to do the same thing. In real life, the more ways we have to do any one thing, the better, because invariably the first one you try will not work. It's, you know, just Murphy's Law. Okay, so what if instead of an amine, we used an alcohol as our solvent and as our nucleophile? Once again, with an acid catalyst, of course, the triangle means heat. Writing HEAT is also fine, of course. And in this case, we actually wind up with 2 net additions of the alcohol, which that's fine. It's also our solvent. There's plenty of it. The initial product formed is what's called a hemiacetal. And then we wind up getting a second addition and losing a molecule of water to get what's known as an acetal. And the definition of acetal is given in this picture. So acetals are compounds of that type. And you can start with either an aldehyde or a ketone. So you may remember in the chapter on nucleic acids, we talked about an NO acetal. And that's the same type of thing, except instead of 2 oxygens, you've got a nitrogen and an oxygen. So in a normal acetal, you've got 2 oxygens there. So that's the definition of acetal. It's a compound of this type. And by the way, it's also allowed to use, instead of an alcohol, to use a diol. And in cases where you can form a 5 or 6 membered ring, I'll bring that up briefly at the end as well. You can actually get a cyclic acetal. So for instance, if instead of an alcohol, we used ethylene glycol, which is 1,2-ethane diol, you would get a 5-membered cyclic acetal. If instead we used 1,3-propane triol, which is also readily available, then you would get a 6-membered cyclic acetal. And that mechanism will be, after we go over this, it would be worth your time to go over that mechanism and try to figure out how that works. Although I'm almost positive that once we make the chapter 19 OWLs available, OWL will bring you through that. I'm nearly certain you will get an example like that. But that would not be wasted time on your part. So what does the mechanism look like? Well, let's consider cyclohexanone reacting with methanol with a catalytic amount of some acid. Again, I could have picked any aldehyde or ketone. I could have picked any alcohol. And the mechanism with the diol is very analogous. I'll maybe give you some pointers as we go through this, but it's essentially the same thing. Just like before, the first step is we need to protonate our oxygen. How do we know what to use to put the proton on? By looking at what we're given. And all I see besides the acid catalyst and the carbonyl compound is the alcohol. So the only reasonable acidic species we've got is the conjugate acid of that alcohol. So that's what we'll use to put the proton on. Once we've done that, we can now have attacked by our nucleophile. Instead of an amine, this time it's an alcohol. And just like before, we have to do a couple of proton transfers. We need to take this proton off, and then subsequently we need to put another proton onto the OH oxygen so that we can lose a water molecule. That's generally the strategy here. That's why we need to get that proton on there. And again, just to give you another example of what not to do, if I may, students will always try things like putting this proton straight onto this oxygen in one step. That gets you all the way over here in one step, and it sounds great because it sounds like you have to write less down on your exam. And it would be fine if it matched up with reality, but it doesn't. That kind of process would involve a 4-membered transition state. And the way you know that is by counting from the oxygen to the hydrogen. 1, 2, 3, 4. So when we say a 4-membered transition state, it means those atoms have to get into the positions of a 4-membered ring, and it's too far away. That's too strained. That's not going to happen. Now, if we had a 5 or 6-membered transition state, then we'd be good to go. Those are very favorable. And I expect if somehow we wound up with an intermediate like that, that proton transfer would happen really quickly, but not with a 4-membered transition state. So we need to use 2 separate steps. First, the alcohol, again, not the alkoxide, right? We don't use CH3O-. That's not going to be present here. The way we know that is because based on what we're given, we're in an acidic solution. And you're not even going to have an alkoxide in a neutral solution. Methanol's pKa is going to be up at about 18 or something like that. So there's no way you're going to have any alkoxide in any aqueous solution. So that's the sort of thing that you need to know, not exact numbers, but that's the sort of thing you need to know to make sense of these mechanisms. Good, so we take off that proton, we get now our hemiacetal, and that's now going to continue reacting. We protonate the OH oxygen using, once again, the conjugate acid of our alcohol solvent, and then just like with amines forming imines, also enamines, we can lose our molecule of water, and this oxygen here actually can help out. Again, I would say drawing that arrow is actually optional. You can just show loss of the leaving group, of the water leaving group, and then what you'll get is just the other resonance form of this species. So that's fine. You'll be able to draw a correct mechanism that way also. Once we form that type of intermediate, of course, we've got a plus charge in our oxygen. Really, that species looks an awful lot like this species, except instead of OH, you've got OCH3. But definitely a very good electrophile. Methanol adds again a second time, and then we get this species. This is just our product, except with an extra proton. We invoke a solvent molecule of methanol to pull off that proton, and we are done. So it's a very analogous mechanism to the ones with nitrogen atoms. And I would say these are all kind of best learned all at the same time. So I still have 2 minutes. Again, all of those structures and arrows are already in your class notes. So I figured it would be easier just to go through the class notes with you and go over each mechanism step by step. When are the chapter 13 owls due? Good question. Not for a very long time, because we still have to go over proton NMR. So I think you'll find it's actually sometime in April. So chapter 13 owls are not due for a very long time. I still recommend, of course, you take a look at the carbon NMR questions. But we're postponing proton NMR as long as we can get away with it. And when we get there, I think you'll see why there was a method to my madness. So yeah, the next ones I expect will be chapter 19. And as long as we finish chapter 19 next week, then I think we'll be able to make them due not tomorrow, but next Friday. Is the lecture from last Monday on the exam, was Monday nucleic acids, or was it amines? It's all kind of a blur right now. But the way you'll know, again, is by looking at the syllabus. The syllabus will always say exactly what's on every exam. So let me move over to this page, just so you guys can stare at those wonderful structures. Let me see now. First of all, open notes. By the exam being open notes, what I have in mind is that it includes the printed class notes. And if you need to look at them on a screen, that's fine. The printed class notes, including any of your own notations on them. And also any separate written notes you made during lecture or while watching YouTube. Anything apart from that is against the spirit of what I meant. And people are asking, can they bring the old exams with their answer keys? It comes a point where it's diminishing returns. You're not going to be able to have absolutely every single thing around and looking at every single thing all the time and finish the exam in time. So what I'm recommending is any separate written notes or while watching YouTube or reading the book. That's fine. There comes a point of diminishing returns. I certainly don't intend for anyone to be looking up things on the internet. Not that I think you're going to be able to look up answers directly. And I, of course, expect that everyone will work alone, using each other as, we'll get to the book. We'll get to the book. Using each other as a resource is no good. In terms of the book, you can use either a hard copy or the ebook. Whichever you want to use is fine. So those are the materials that I'm intending for you to use. Also, and also, please, your cheat sheet. I hope you're all making a cheat sheet. I think it will only help out. You know, 1 or 2 pages of a digest of what's on the exam. Try not to use, real mouse print, bacteria print, whatever you want to call it. Be reasonable about it. You want it to help yourself out. In terms of ways that you can take the exam, you can either print it off. Okay to leave the room while you do that. And you'll just write it as usual. Then at the end, you'll scan or photograph. By the way, all these instructions I'll also make available with the actual exam, but I just want to assuage some curiosity. Scan or photograph, convert to PDF, submit to eCampus. That's one way you can take the exam. Another way is you can take the exam on a tablet or iPad, and that's generally pretty straightforward. You'll again convert to PDF, etc. I can't say I've had anything like the majority of the students taking exams that way, but it's also not one or two. It's a significant minority, and that works just fine. If you do not have a printer or an iPad or a tablet, then you can write out your answers on separate sheets of paper. You do not have to copy all the questions. In that case, just write down your answers. The only thing I'll ask is that you use a separate sheet for every page of the exam, and that you include the point rubric or point breakdown, whatever you want to call it, on page 2. Of course, also you'll be given a periodic table. I go PT for periodic table. You may use a calculator if you really want to. I mean, there's not going to ever be anything in our exams beyond simple arithmetic. So I don't think you really need a calculator for that. At the same time, I would feel awful if people lost points merely because they didn't have a calculator. So if you want to use a simple calculator, you certainly may. Let's see. So I covered the book. I'll make the deadlines clear at such time, but basically you'll have class time or maybe class time plus a little bit. Usually I consider our exams to be about 55 minutes. And after that, class will be over. But if you have another class after this, there's still half an hour to get from one place to the other, during which you can do all the photographing or scanning, converting to PDF and all that stuff. The best resource in terms of which PDF conversion software to use is each other. I'm not going anywhere near the classes webpage. Will you have time before the official exam time to print off the exam? I don't know if it'll be before, but what I'm saying is after the class ends, you'll have time also to convert. I usually give about 15 to 20 minutes total extra, and I will make the deadline clear. And yes, if you miss the deadline by just a few minutes, it's fine. If you miss it by 2 minutes, please don't email me begging me not to lose points. It's fine. We will ignore it. 2 or 3 minutes is fine. 20 minutes is probably not fine, right? Half an hour is decidedly not fine. A few minutes is fine. We'll ignore it. Now, those of you who have, I'm sorry, I've stopped typing, but I want to be sure I get all this out. Those of you who have accommodations will have later deadlines, and I will make it clear at the time when those are. The way to estimate what those will be is you figure 55 minutes plus maybe another 15 is 80. So multiply that by 1.5 is 120, right? So that's how you can know approximately when your deadline's going to be. Other than that, I think that's about it. I hope everything will go smoothly. Do expect, I guess a couple other quick things. Do expect that there will be issues when you're submitting your exams. eCampus has been known to get kind of clogged. It may take several tries. One thing I'm going to do differently from last semester is I'll give you unlimited submission attempts. You can try as often as you like. And just keep trying until you get a version in there that you're happy with how it looks. But do double check it, triple check it, etc. Do you need to do it again with more contrast? That type of thing. But you know, once you're satisfied with how it looks, you're free to go. You don't have to say anything. You can just leave. The last thing I will say, and this is super important, when you're done with the exam, regardless of what happens, keep your exam. Please keep your exams, just in case. You know, sometimes strange things happen that are the fault of no one in particular, but just in case, keep your exams at least until they're all graded and everything's all done. We'll try to get the grading done within about a week. It all depends. We frankly have not finished on the, I don't know if we've even started on the Organic 1 exams, but we always try to get them done within a week. That's what we aim for. Other than that, I'm well over time, so have a great day. I'll see you all on Friday.